Hi, everyone. Good morning, good afternoon. We have people from different time zones here. So thanks for being here. We are very excited having you here. We are expecting a lot of people, over 100 people subscribed, and there will be a nice number of people today. Hopefully a very good discussion as well, because it will not only be presentations, it will also be about your questions. This is a very good moment to discuss a bit. Um, so welcome in this webinar. We will introduce ourselves and I will introduce myself a bit later. So this webinar is about smarter process design with CFD simulations. So CFD, computational fluid dynamics, are these nice, very nice, colorful drawings. Most of you have seen them in the past. We will be really giving a lot of examples in this webinar, how they can be useful in the water industry across many, many different applications. So let's get started. First, we will start with the objectives of today and the content, because we are very honored that you are willing to actually spend like an hour here of your precious time. So we also thought well about the content, how we can make it most effective for you, and can we give you a very good overview in this 1 hour. So the objective of today is, by the end of this 1 hour webinar, you are aware of how CFD can be helpful in your case, the why and the who of CFD. Yeah, who can it be used for? Why should we be using it? What can be the benefits? But also that you are able to make best use of it in your specific situation, because there are so many different application domains of CFD. And this resolution is also something we will try to provide here. So what are the different phases or the different types of projects CFD can be used in? The target audience, this is really a very important message on beforehand, is for non-CFD experts. Of course, it is useful for people having CFD backgrounds, because you will also see a lot of practical case examples, but we will not show too many of the mathematics or the formulas behind, okay? So it's all about the practical applications. We will be showing the needs of different stakeholders. We will show a lot of case examples, because this is in the end what makes things very clear, the practical application. And also we will end with some common misconceptions or some things you should really know about CFD. So this is where we will end with. Of course, throughout the whole webinar, we have ample of time for Q&A. So we will do live questions and answers. So if you hover over your screen, you see a Q&A button. If you hit that button, you can actually ask questions. We have moderators here that will be continuously watching the questions. And if they are very relevant, we will be answering them live, okay? So don't hold back. You can also decide to answer questions anonymously, okay? Ask your questions anonymously. So don't hold back. You can do perfectly anonymous if you don't want your name to be shown, for example. We have two presenters here, one moderator, and a couple of other people I will be introducing them very soon. After this webinar, there will be a short questionnaire, because we are very interested in hearing your thoughts, and also we want to continuously improve, and we want to look for the next topics. Okay, let's start with a very, very short introduction. I am Wim Oudenaert. I'm a CEO and co-founder at AM Team. So what is AM Team? AM Team is a company providing advanced modeling solutions to the global water and the process industry. In the meantime, we have a very nice team. We are quite proud of all these people here. Quite a fast-growing company. So you can see that we grow on average 100% a year. We started this company from Ghent University, actually. This is officially a spin-off company. And then most of the people in our team working on the simulation side are either environmental engineers or chemical engineers, okay? But we also have different profiles in our company working on finance, marketing, and other things. Who are here today? So I'm Wim Oudenaert, CEO, co-founder of this company. And my background is environmental engineering. I have both a master's degree and a PhD in that. We also have Usman Rehman. He's my fellow co-founder. He's the CTO of this company, and Usman has a huge amount of experience with CFD. So he has actually built his career on CFD and now heads up the whole engineering team in our company. So Usman has done a lot of yeah, kinetics and CFD, multi-phase CFD, and things like that. We also have Celia here, Celia de Wilde. Celia is business development manager. Celia will be continuously looking at the Q&A here, and she will also bring questions forward from the audience. So Celia works with a lot of customers internationally. And we also have Willem here. Willem is our marketing communications manager. So he joined our team to build the brand of AM Team further internationally, of course. And then we have also Peter that is joining this webinar. Peter is solution engineer as well. He's in the team of Celia and working with a lot of customers internationally in the water industry as well. So these were the introductions. What we typically put on the slides is also our customer ratings. Because we are a simulation company, we are not doing anything else. This is our core focus. And the only way how you can actually serve the market is by providing value. And the only way how you can prove value is by customer ratings. So our customers are very, very happy. This is what you see on these numbers in terms of expertise service. We really want to stress this because simulations for quite some practitioners can still be a bit of abstract thinking. Yeah. Why do we exist? Well, our company, this is our why. We challenge the status quo in process engineering for optimal use of resources. It's quite simple, quite practical, pragmatic, but there is a lot of things behind here. Resources can mean literally your resources, energy, chemicals, but also it can mean time you put in testing, time you put in operational costs, CapEx, so capital expenses, but also man hours or the number of people. Resources is really broad here, okay? We use simulation to really make optimal use of resources. These are our customers. Well, some of our customers, we serve 3 main categories of customers. We have the end users, operating processes, for example, water, drinking water utilities, wastewater utilities, big chemical companies or pharma companies worldwide. So they are really operating a lot of processes and have optimization challenges. Then we have design companies. So design like technology vendors, technology designers and developers. And then we have also consultants worldwide asking us to join projects. We are headquartered in Belgium, but we have a global reach. So you can see that we have actually projects all over the globe. And we have, our core unique strength of our company is a combination of cutting edge simulation capabilities. So we are very good at simulating, but also we combine it with very good process understanding. And this really leads to a lot of difference and the best solutions. Okay, good. Let's start with the basics of CFD to get everybody up to speed because this is quite important to grasp. CFD is a computational fluid dynamics. It's a physics tool. So the core of it is physics equations, and you use it as a structural simulation tool. So this means you are not really doing trial and error process optimization. You are really structurally looking at your problems and then trying to solve them. One example is this system. This is an existing wastewater treatment reactor. It can be any system. It shouldn't be a reactor. It can be any system, like a membrane or a big intake for drinking water. It can mean different things. The first step is you build a 3D geometry. Typically, it's not too difficult for us. It's a very simple geometry, but it contains very important elements such as mixers, propellers, aerators, if they are there, your real geometry and dimensions. We do the meshing. So meshing is dividing this whole domain in little cells. In each of those little cells, equations are being solved. And you can have, for example, for a full-scale installation, easily 1 to 2 million of these cells. Luckily, we have very good computers leading to very good simulations in reasonable time. And then you get the output. What the colors mean will be explained throughout the webinar. It is not only mixing. It is not only telling you where dead zones or short circuiting happens. It also tells you where local dissolved oxygen is, where particles are accumulating, where the shear is on your membrane. So the colors are a whole bunch of different possible variables, okay? It really depends on your objective and your case. This is the most interesting thing of CFD. This is the what-if scenario testing. Just imagine you have all of your oxygen accumulated at the inner side of this reactor, which is happening. This is the red color. The red color indicates your local dissolved oxygen. In the same zone, the other side, you have less dissolved oxygen. Ideally, in a reactor zone, you want to distribute it evenly. So then you can do these what-if tests. This means, what if we switch off some of the mixers? What if we would move some of the aerators upstream? Things like that. Things you can actually never test in practice or in reality. You do these tests, you look at the output. Some of the scenarios give you much better performance. For example, this one. In this case, we could also switch off some of the mixers permanently. And in the end, you end up with a best design. It is this design that you will really build in practice or implement in practice. So this is really conceptually the core of the value of CFD. So when can we then apply it and who can benefit from CFD? That is the next question, yeah? So we have identified 3 main phases, and each of you might be working in one of them or multiple of them. So we will be explaining which stages we can implement CFD in, the services we can offer, and then the needs we can actually solve or meet with those, okay? The first one is R&D stage, mainly for technology and technology developers and vendors. They are interested in virtual prototyping and the scale up of novel technologies. So the time to market, for example, is a big issue, and you want to scale up as fast as you can. You want to have the optimal design of a new technology before you burn all of your money in expensive piloting. So that's a very important need here. If we look at the process design, here we are talking about detailed unit process design. For example, where do you put certain baffles? A baffle wall? How do you configure optimally your inlets, your outlets? Would it make sense to change the bubble size? Should we actually change the filling degree of our fluidized batch reactor? There are many, many possible questions here. So it's all about dosing efficiency, baffle placement, mixing, system performance. When your system is in operation, of course, we are using also CFD to troubleshoot and to optimize or retrofit the process. This is what we call virtual process optimization. Again, similar questions about dosing efficiency, baffle placement, mixing. So testing things you cannot really test in practice. Okay, so these are the 3 core phases, and we will be giving throughout this webinar examples from each of those phases. To make it very concrete, what the practical applications are, well, this is an example from the R&D stage. We had a Japanese customer, Maezawa Industries, that had developed this new MBR technology. This is an MBR, membrane bioreactor. There's a membrane inside. They had actually a 3 cubic meters pilot running, but they wanted to scale it up through 2 orders of magnitude to 100 cubic meters demonstration scale. So yeah, then you can choose, do you put an extra pilot in place of 10 cubic meters, 20, 50, or do you take the CFD route? This is what they have done. Working with us, we have built the CFD model of the pilot. We've scaled it up. So the color gradients you see in this simulation, this is a side view of this reactor. So we are looking at the vertical cross section. This is not the mixing, but this is, for example, ammonia, the ammonia gradient in your reactor. At the bottom, you have high ammonia in the system. The dark blue zones indicate low ammonia because there is a lot of oxygen. Yeah, so we scaled it up, and in the end, you test different design scenarios and you end up with the best design. Such a model has a direct coupling between CFD and kinetics. It gives you not only the mixing, but it gives you the concentration gradients in 3D. So it also gives you the permeate quality in this case. And the best permeate quality was from a certain design, the design that has finally been built. So this is currently operating in the vicinity of Tokyo in Japan. In this first stage only, these people saved around 150,000 euros, but we are now in the second stage going to 1,000 cubic meters. But they saved over a year in this stage. So you can see that we tested 5 designs in around 5 weeks of time. Another very nice example, which we use often, this is from the design stage, is this example where people wanted to introduce pure oxygen aerators. This is the top view of the system. 2 injectors left and right. You can see the mixing speed, which is the red color. There's a dark blue zone, which is bad mixing. We slightly shift the mixers or the injectors. 0.5 meter, we're rotating, and then you see the whole system starts moving. So this is the same mixing energy that is used here, but it leads to much better mixing by simply moving these mixers with 0.5 meter. So this is a case we use very often to illustrate the sensitivity of system design to very subtle decisions you take. Yeah, they could actually save an external recirculation loop plus a pump, and they of course reached process performance that was optimally, but also they the bubbles traveled a bit longer, so the transfer efficiency was also maximized. So a lot of gains to be made actually. We will start with the first poll before we go to my colleague Usman and dig into a lot of cases. So Celia, are you able to launch a first poll? Okay, perfect. So okay, we have 2 polls here. So it would be great if you could indicate how familiar you are with CFD, and also why do you attend this webinar? What are the main drivers for you? So we will give it around like 10-15 seconds, and then we will look at the outcomes. So Celia, you can end the polling if you see a significant fraction of the people have voted.
Yeah, I'll give it just a few more seconds, and then I think we can continue.
Okay, we can actually look at the results.
Yes.
So, okay, very interesting. Most of the people, let's say it's 70% or 60%, have limited experience with CFD, and some people have used CFD in the past. It's like 1/3. And most of the people are interested in having a general overview of the applications, which is very good because this is the goal of this webinar, and also interested in CFD for process optimization and design. So these things will be, and scale up as well. These things will be tackled in this webinar. So this is very good. The target audience is a very good match with the content of this webinar. Okay, so before we enter the cases, one more slide on a successful CFD project. To us, a successful CFD project means a CFD project that can, of course, solve your problem or help solving your problem, but also within reasonable time. But it's not as straightforward. Huh? You need to have certain quality met. This means you need a team understanding the technology, being able to do it with experience. Yeah. You also need a speed of execution. So people have preferably experience with this similar technology so that it doesn't take months, but you have your results in a very short time and you can iterate a lot of scenarios in a reasonable time. And then you need to have the availability of experts. So the critical mass is also important when you have a question that it gets solved or that it's, that people start solving it very fast. Yeah. So this is really very important. This was the core philosophy behind launching our company, and we wanted to be really in the sweet spot. Okay, this is why we are building a focused team for the water industry, but also a very big team of people that is growing. Of course, I was talking about the needs, but you have these different stakeholders, these 3 groups: technology developers and vendors, consulting and engineering firms, and then end users. The 4 big categories why you would be using CFD are these 4. It's about cost saving, it's about time saving, you want the optimal process performance, and you want to have more confidence and new insights. These 4 categories are always at play in projects. But specifically, these groups also have some subtle differences. Huh? For example, if you are working on the development of a new technology, the time to market is more important for you, or also to save scale up and experimental costs, or to be able to test more designs. For consulting and engineering firms, speed is very important. So they want to save time in the project, and the speed of execution is very important. They are looking at the end customers and they want to gain some competitive edge. That's why some of them are hiring us. But also, of course, you are designing systems based on engineering rules of thumb, and you want to have them confirmed. And then if you look at the end user, it's all about the process itself. Can we save energy? Can we save OPEX? Can we maybe build this plant a bit smaller so we can save CAPEX? And can we have optimal performance while doing the other things? So this is just to summarize the main findings. Okay. In the meantime, if there are any questions, feel free to ask in the Q&A, and then Celia will be coming back to them. Okay.
Yeah, maybe Wim, if I can just jump in. I saw one of the participants raised her hand, so I'll let her maybe ask her question. Esther? I think, yeah, just I'll ask to unmute.
You can always ask the question in the Q&A, yeah, if there is something left. Yeah. So I will now give the floor to my co-founder and colleague, Usman. He will be digging into the case examples.
Yeah, thank you, Wim. I don't know if we still have to get this question, Celia.
Yeah, I don't know, Esther, do you want to ask a question or not? Because I saw your hand. Maybe it was a typo. I suggest we continue, and then through the chat or the Q&A, I can help.
Yeah. Okay. Well, as Wim explained, there are different stakeholders which might be interested in different applications of CFD. So we have divided our CFD cases into different types of projects. So first type we'll touch upon is detailed design. So how we could use CFD simulations and modeling in detailed design. Yeah. Okay. Yeah. All right. So the first case is actually of clean water storage basins. So here on this slide, actually, you see on the left side a CFD simulation, and on the right side, tracer concentration at the outlet of the basin. Why we have put this slide on the show is that normally this is a common practice in the industry. If you want to optimize your basin, if you want to optimize the mixing in your basin, you would like to do a tracer test and see the concentration of tracer at the outlet, like really physically doing the tracer test and calculating baffle factors to evaluate the mixing. But what CFD can do, actually, you can do the same thing in CFD. If you see in this simulation, there's this inlet of the tracer, and then there's the baffle in front of it that kind of uniformly distributes the tracer coming in, and then there's an outlet, and you clearly see there's a short circuiting happening towards the outlet. And you would see it in your baffle factor calculations, in your tracer concentrations at the outlet. But what you will not see in physically is where the dead zones or the bad zones are. So how the tracer is actually short circuiting towards the outlet. With the help of CFD simulations, you can actually perfectly see where your local dead zones are or how your tracer is distributed. And based on that educated knowledge, you can actually further optimize your basins. So this is a very good and practical example I just wanted to show first. But of course, you don't have to do all the time the transient simulations where you have to look at the tracer in time. Rather, there are other alternatives where you can look at them in a bit more steady way. So in that respect, we have another example of clean water storage basins of Pitpa. This is a water company in Belgium. And in this case, we were looking at their water storage basins, like 4 of them, which were hydraulically connected. And they had some inlets and some outlets in different parts of the basin, depending on their usage. So what we tried to do was to look at their proposed design. So it was still actually before they built it. So we looked at their proposed design and tried to figure out if the mixing was optimal. We tried several designs, almost 15 designs in 4 weeks. And then we figured out during the simulations that actually the baffles placed to improve the mixing were not really helping the mixing, rather deteriorating the mixing locally. So if you see, for example, in this section, you see that there is no new water coming into the section because of these baffles. It's actually a large dead zone. But if you remove the baffles, you actually get much better distribution of your water. And even though you have active inlets and outlets at different locations, and if you can keep changing them, even then there's no huge impact on the mixing. So in this case, they were able to save a lot of capex by not actually building the baffles extra walls inside these basins. So this was a very good good case example. Another example is of sand filter, rapid sand filter designs. Rapid sand filtration has two normally steps. One is where you are inputting your influent from the top of these, and then collecting all the pollutants on the bed of the sand bed, and then the clean water going through it. And then the next step, you have to clean the bed by backwashing, by introducing water and the air, or combination of both, from the bottom, so you can actually get rid of your pollutants which got captured in the first step. So this is the simulation we did for the backwashing step to see if the sand was enough fluidized and if there is no short circuiting. And actually, the larger goal of this case was to see what would be the impact if you have a circular sand filter or a rectangular sand filter, and what would be the impact of inlet structure or the height of the sand bed and different operating conditions. We tested 4 designs in almost 4 weeks. This was a transient simulation, which means it ran over time. What you can see here on the left is a sand bed fluidization during the backwashing. You can clearly see that it fluidizes. Now this is just the water, but then you will have air coming in, and you would see clearly a bit more fluidization, even some overflow into the outlet gutter. You will see right here. So actually, what we found or figured out, there was no huge impact of these 2 designs. So you can actually use the same. You can actually use either of them, but there is a huge impact of actually inlet. So how you configure your inlet, if you put it on the sides or in the middle, or another way, you might have an impact on your fluidization of the sand bed. Another very important finding, which was also kind of confirmed from another client, which were emptying their own sand filter, that they saw some dead sand around the corners in the wall, close to the wall. We also found that same situation in our simulations, which kind of confirmed our also hypothesis that you need to have much even distribution of your backwashing spargers at the bottom. Okay, another example is of a pellet softening reactor. This is also for a drinking water company in Netherlands, Wittens. In this case, they were first looking at how their current design is operating. Is doing okay? From performance point of view, it was already working very efficiently, but they just wanted to know if there are things which can have a huge impact for further fine-tuning their pellet softener. In this case, they wanted to, for future installations, they wanted to reduce the capex and be more sure about the performance, and also possibilities to reduce the size of the reactor, and also keep it optimally fluidized. So in the pellet softener, you have pellets of different sizes, which are in the reactor, and then you have water coming in from the bottom to reduce the hardness of the water. And the idea is to have them as much as possible fluidized and as much as uniformly across the whole depth of the reactor. So on the left, you'll see a small visualization of the pellets. It's just not the whole particles, of course, there are much more particles, but it just shows you how actually CFD can help you in visualizing such systems. You can see higher velocities at the bottom and very slow movement of the granules or the pellets at the top. And this is very much kind of intended with the design, where you have a smaller diameter at the bottom and higher diameter at the bottom at the top, so that you can you don't overflow your pellets. So so here you actually see different particle sizes distributions, how they are distributed in the pellet softener. So you, as I said, there are like several sizes in the pellet softener existing. So we tested all of them all together. So in this case, you see ranging between 0.25 millimeters to 2 millimeter pellets. And you clearly see that 0.25 millimeter pellets were much more uniformly distributed across the depth of the reactor, whereas the more the higher the size, they tend to stick more towards the bottom, which means it's harder for them to get them completely fluidized. But this was also very much in line with the findings in the measurements, because when you take the sample, you clearly see that the larger particles always tend to stay more close to the bottom, whereas the smaller particles tend to stay at the top. By using this model, you can actually, for future, you can further improve the design by changing, for example, height of the reactor, finding the optimal diameter gradients across the depth or the height of the reactor. It can be a very good model in that respect. What we are currently doing with this model is we are actually helping to improve the digital twin model, which Vitens already have worked on, to include really the precipitation of these of the system. What we are doing is we will provide them with the more realistic flow distribution. So because if you don't have the CFD simulation, you cannot like predict, okay, if your system is really plug flow or it's more like a CSTR at the bottom. So the network of the flow can be driven from the CFD simulations, and that's where we are helping Vitens with in creating their next level digital twin for this purpose. Okay, so this was another example, and then another very important example could be industrial and municipal wastewater treatment plants, where we use CFD biokinetics, which Wim also mentioned, that the kinetics can give you much more insights about your system, not just looking at the velocities or not just looking at the mixing in general, but also looking at the process performance in terms of, for example, CFD removal or dissolved oxygen, nitrates production, or ammonia removal, or in the case of fermenter, it could be volatile or fatty acids. So here you see like 3 different examples, but they follow the same procedure, that you actually do the CFD, and then on top of that, you integrate kinetics. And this kinetics can be any kinetics. It doesn't have to be only nitrification or denitrification. It can be N2O even, or by a P removal together with the hydrodynamics of the CFD. What we can achieve with such simulations is that you can first actually really look at the impact of the process, impact of your configuration on the performance of the process, and then by tweaking, for example, you can choose better mixer selection, better mixer, or you can choose to have a different mixer, or choose to have it at different location, and see what would be the impact on the performance of the process. You can have different aeration designs or entirely new reactor designs, or for example, in case of chemical dosings, you can have applications also evaluated with respect to how a process will perform. So this opens up huge possibilities in that respect. Okay. Then this is another example, which is a recent project going on. It's an industrial wastewater treatment plant where we have a denitrification reactor, and it's of course it's without oxygen. It's just nitrates. A rich nitrate stream is coming in because of this because industrial waste stream probably. And then what we see here with the help of biokinetics is that there is a huge short circuiting happening from the rich nitrate stream towards the outlet, which then eventually will go to the aeration tank, and there will be more nitrates produced because of the nitrification, and this might be a problem for the overall performance of the plant. So this was a very good example where we could see the short circuiting when we actually when we actually updated our CFD model with the biokinetics. This was not so much visible when we didn't include the biokinetics. So this is a very good example where biokinetics really aided in figuring out what was causing this problem. One of the solutions which is still under evaluation is how maybe we can just change the mixer angle so that we don't push it towards the outlet, rather maybe more towards the middle section of the reactor to avoid this critical short circuit. So this was another very practical application But yeah, actually, if you look at industrial plants, there are several several needs. One of them, of course, is the mixing in the anoxic zones where you don't have aeration, you have mixers, and pumping and mixing costs are quite high. And not only cost, but you also have to make sure that you have very good performance in those zones, which can be very critical. So CFD can definitely help in figuring out the mixing in the anoxic zones and also optimizing it. Another very important factor here is the chemical dosing. So if you are dosing chemicals, where you should dose, how you should dose, what should be the strategy. The CFD can really help in determining the strategy of chemical dosing. Another new trend is about pure oxygen systems being used, where we expect that the mass transfer will be much more efficient because it's pure oxygen compared to air. But the downside of that is that once you use the pure oxygen systems, the gas flow rates are normally lower than normally you have in the aeration system where you have air, which means that you might end up actually with lower energy inputs because of lower flow rates, and which might lead to lower mixing. So it becomes very important to have this overview using CFD on the mixing. And also determining good mass transfer between the two phases. So CFD can definitely help you in determining the right configuration of your pure oxygen injectors, flow rates, angles, distribution. This was also an example which Wim showed with this short video, where we just changed a little angle and we were able to get much better mixing in the system and the DO concentrations. Okay, so that was the detailed design part. And now if we look at the technology development part, where we have a few more cases. So this is actually a case where we modeled tubular membranes. So what happened in that case, the client was actually, they found a new design which was actually performing better, but they didn't know really why and how much, and can they really use that as a common design in their the new design they found was this helical ridge structure inside these tubular membranes, which eventually led to less fouling or deposition of solids inside the membranes. So they wanted us to know, to see and calculate why it is working better. So we actually modeled both. So one without the helical ridge, one with the helical ridge. And we figured out that actually with the helical ridge, you end up with higher shear. With higher shear, you tend to remove the deposited particles, or you don't even let the particles to deposit on the surface of these membranes internally. So you can see on the right side, there is this Riemann open curves of shear stress over the surface of the membrane area. The orange curve really shows you the helical ridge shear stress, where the blue shows you the plane case. And you clearly see that in the helical ridge case, you had higher shear over the membrane, so which was eventually causing better performance of this tubular membrane. So they were able to actually conclude that and take it up further. Another example in terms of technology development is the design of a novel electrochemical reactor. In this case, the idea was that they have these particles which they wanted to be suspended much more evenly. They had an idea at a very small scale, at a lab scale, to build it, but once they built that little lab scale prototype, they saw that they were not able to actually make these particles suspended or fluidized. So we took up from CFD point of view and started implementing it. We already started with a bit of an improved design, so that we can see if we can already get some improvement. But what we saw, if we just took that input, we saw that the particles were really falling down. They were not really fluidizing. We tried different ways. So like we tested 6 different designs almost in 4 weeks. So I will just show you a couple of iterations. So this was the next design we tried, where we actually, instead of pointing the flow upwards, we pointed it downwards by designing a certain inlet structure. And we saw that now we got the fluidization, but it was too much, and it was not very symmetrical, which was also not desired, and it will also lead to flush out of the particles or floating of the particles at the top. So this was kind of overkill. So we needed to kind of lower it so that we can have the optimal mixing or optimal fluidization of the particles. So what we did in that case was we changed the inlet structure further. Instead of bringing it from one side, we brought it from two sides, had a baffle in between, still pointing downwards, and tweaked a bit of the flow, incoming flow, and then we eventually saw better distribution and the better particle fluidization in the reactor. So this was a very good example where we started with an idea on the paper, and we gradually iterated towards an idea which would eventually work. And this actually was implemented eventually in the lab scale, and we clearly saw that all of a sudden, with this little tweak in the inlet structure, we were able to get the required performance of the lab scale reactor. And now they are working on scaling up, and we might be involved. Yeah. Okay. The third case or the list of cases is about optimization and retrofitting. I will start with the with example of a homogenization tank where the client was looking at screw-wide accumulation in their reactor, which was of course not desired. And they only had a couple of impellers on the side like this, one impeller here, the other here, but there was a lot of accumulation happening in the middle bottom. So what our first reflex was to actually go ahead and maybe install an impeller or a mixer in the middle so that it can actually get rid of all the accumulated screw-wide throughout the reactor. So we tried that and eventually led to further iteration by changing some angles of the impellers to get to the final design. We again tested several designs, like 6 designs were tested in 6 weeks. And the next slide, you would see it's three different cases. So the base case is where we only had side impellers, and you would see here that the screw-wide was really accumulated at the bottom. And then if we installed a central impeller, you would see that the screw-wide would start getting more uniform, but still they were like not the best. And then the last time we just tweaked the angles of the impellers a bit to make the both impellers in sync with each other, so that the flow is not acting counteractively against each other. So I will just play these animations. You can see the impact. All right. So here you see not a lot of movement is happening because actually these screw-wide just stay there. In the middle, you clearly see that now the distribution is happening, but it's actually, again, it's kind of stuck at the outer bank of the reactor. Whereas in this case, now everything is working in harmony. So all the particles are moving in very good synchronization. And then, of course, you have very limited settling or accumulation of the screw-wide in this case. So this was a very good example. And now currently our client, Zealand, is already implementing this strategy. Yeah, so impeller type was checked and positioning was checked, which is very critical for the energy consumption. And this is another example of a full-scale secondary settler in the utility of Kalamazoo in US. The question was they were looking at the secondary settlers. They wanted to increase the capacity of them, but they were not sure if the current design would hold up. So our task was to actually first do the simulations and see if the current design is optimal, and maybe increase the capacity and the loading on the settler and kind of try to optimize the performance under the high load conditions. The first outcome of this project was already that we found out that we tested actually in the project to do 2D simulations, which is a very conventional way or very common way in the settling in the CFD modeling of settlers. We found already that actually if you would do 2D simulations, you would have a lot less freedom and a lot less accuracy in predicting the sludge bed height. So we performed 3D simulations of these settlers, and we had all the freedom to actually change whatever baffle, whatever inlet design, whatever outlet design to get the best performance of the settler. In this case, we tested almost 8 designs and took almost 10 weeks to test. This was a special case because they were like dosing some chemicals to actually further improve the settling. So this was also taken into account in our CFD model. and then it was also validated with the measurements, as you can see on this slide. And here you see a couple of results. So the scenario 1 was actually the scenario, the base scenario, and then the scenario 5 was eventually the last scenario, which was found to be optimal. In this case, we tested different designs, and when we see at different options with respect to design of the settlers, we can have, like, for example, different inlet structures, different baffles, energy energy dissipation baffles, and different outlet structures. And yeah, there are always some difference in the capex. So one option can be expensive than the other. One very good outcome of this project was that we were able to find a solution which was more optimal but less expensive, which eventually, of course, reduce the risk of actually having higher capex if you would have gone with a higher priced option. So this was a very good outcome, and they are already now implementing profits on their plants. Okay, so if you have any questions, please go ahead.
Yes. Thank you, Usman. There was a question about how we choose the designs we will test. So in general, I think it's in accordance with the customer, what is feasible on site. For example, the ADIs, there was a definite number to be tested. But then an additional question came if we also use from time to time search-based optimization or parameter sweeps, or is it always human-made design choices? Maybe you can elaborate a bit on how you approach this in our project.
Yeah, the first question, Celia, indeed, it depends a bit on the problem at hand. So normally, if you are working at such a large scale, like as I said about these large settlers, you don't have all the freedom. So normally, client has some freedom, and they always suggest us, okay, guys, we have these things we can change, and these are the things which we don't want to change because they are either expensive or they're impractical to change. And then we know, okay, what are our degrees of freedom, and based on that, we can propose some design changes, and we can test them and let them know, okay, which works and which would not work. Same, for example, for the homogenization case where I showed, like, we installed 3 impellers instead of 2, and we suggested to change the angle of 2 existing impellers. So there, we knew from the beginning that we have the flexibility to add 1 central impeller. It was our freedom to have what type of impeller or what RPM or what motor should be driving it. And also we had the freedom to actually change the angle of the external impellers, or even change the impellers altogether on the outer side of the reactor. But nothing else. We couldn't change, for example, inlet location or outlet location. But this is something which client was able to tell us. And based on these limitations, we were able to give them the solution. It might not happen that you get the best possible solution given your limitations, but even then you can have the best possible solution within the limitations of your system. So that's the first part. The second, Celia, about the automatic. I mean, the question was more about if we let the model decide where you should have the optimal setting, or we always do a human decision to choose that. Sometimes it's very hard to already do that at such a large scale. This is possible, but we hardly do it because normally we have so many constraints. It's normally much easier to do in a human way. But this is certainly possible, and if there is an opportunity, we definitely try to do that, where we let the model choose the best optimal location of a certain configuration. Let's say, for example, if you're testing different RPMs of the impellers, we can just ask the model to iterate at different RPMs, and the model can let us know, okay, what RPM would be the best, for example, or different inlet locations or baffles, definitely.
Yeah, there's another question about the verification of our models, but I think Wim will answer this later on. Yep. So I think we can continue with the presentation.
Yeah. Okay.
Okay, so thanks for the questions. Thanks, Usman, also for showing us all these cases. We will continue a bit, and of course, we have more room to answer more questions. Huh? So yeah, one other question was that, and a question that keeps reappearing is, do you verify your models, or how is it with model validation? Well, I can give a very clear answer on that. in 95% of the cases we are doing, we are not validating our models anymore. So this is a lot, right? So it means you don't have to use any measurements in 95% of the cases. Why? Well, we have been developing a lot of own models. They have been validated extensively in the past. And if we keep using them for similar applications, we don't revalidate anymore. What are the remaining 5 to 10%? Well, either we are actually rolling out a new model that we never have tested before. In that case, we want to validate it. We also continuously develop new models, so that this can be the case. Or second, the customer might insist. So some of our customers insist, and of course, we also go with that if it increases the confidence in the project and if the data is available. Yeah. So the answer is yes, we verify our models, but not for every project, and it's only a minority of the projects where we do new model validations. We can provide you with more information on that specifically, because we even have published a couple of papers on this topic. So these are some common misconceptions and questions about CFD. One of the very important questions is it possible to simulate my system? Well, I hope we could illustrate a bit that many things are possible. So we are talking about one phase, water only, or two-phase systems, mixtures of water and gas, mixtures of water and solids, or three-phase even. One example Usman showed was the sand filter, a backwashing of the sand filter bed with water and air, lifting up the solids, which are the sand. We have anaerobic granular sludge systems that are also three-phase systems. We can simulate special viscosities, the coupling of CFD and kinetics, and also the size can be from very small size or scale. One example is these tubular membranes to a kilometer or millions of cubic meter scale. Examples are these big basins. For example, this basin on this picture is like 200 to 300 meters in length. Yeah, so it can be really a very wide array of applications. What is the time that CFD takes? We have been always indicating the time in these cases. So typically we are talking about weeks. But yeah, bear in mind that the simulation work only would, in most of the cases, take only 1 week. But of course, we have intermediate discussions. Of course, we have intermediate reporting. And of course, we have some discussions about the data and about the simulation scenarios. So all of this together, well, typically we are in the order of 4 to 6 weeks. Time gains are significant, so they are months to years often. Years, especially in the scaling of projects. This is a wide overview of projects in the wastewater field and the resource recovery fields we have experience with. We have not shown all of them. The ones we have shown are these ones. So nitrification, denitrification, MBRs, secondary settling. But you can see that we have been working on coagulation, on dissolved air flotation, on phosphorus removal, crystallization reactors. It can be a lot, right? So oxidation, ozonation, digestion, and even MBBRs, where you have these carriers. So these little plastic carriers floating around in your system. Major questions here are mixing positioning. How do you pull back the carriers? How do you avoid that they all accumulate at the end near the grids of your system? So all relevant questions. Similar for drinking water, we have been showing some of them, like pallet softening, disinfection and storage. We touched a little bit on membranes and rapid sand filtration, but again, you can look at large surface water storage basins, advanced oxidation or disinfection with ozonation, UV disinfection, ion exchange, and many more actually. So this is just to give you a wide overview of all the technologies. Another very relevant one is, what is the cost and the payback time of CFD? It often comes back as well. So just to give you an indication per stage, these are ballpark ranges of projects. So we work on a project base. Typically, for some of the customers, we have service contracts for recurring questions. But typically, we are talking about such ranges, just to give you an idea. I know it's a wide range. Some projects are even bigger, but the vast majority of projects is in between these ranges. Yeah, this is in euros. Typically, the technology development projects are at the higher side because you do a lot of scaling up, virtual scale up. It's much more intensive, such projects, because we are co-developing with the customer. Yeah, so these are ranges typically, I would say, for design optimization projects, 15, 20, 25, 30K are typical ranges. Yeah. If we do payback time calculations, typically it's a few months to less than a year in terms of energy savings or experimental savings for many of our projects. But of course, you have some better nights. Simple examples we have shown was this baffle wall that the drinking water company has not installed in the end. Yeah, it was like 15K per baffle wall, so that amounts to 30K. Well, if the cost of the project is less than 20K, only saving this baffle wall is already very interesting. But of course, the main focus was the performance, the storage and the mixing. Yeah, if you can save a year of piloting, of course, you save over 100,000 euros easily. And we had a couple of plants where we could switch off mixers. One of the plants in the Netherlands, we could switch off 6 of the mixers. If this is a large plant, yeah, that leads to a lot of energy savings. Yeah, payback time only there was 1.5 years. But in the end, the main outcome was the effluent quality that improved. So nitrates, especially. So this was to answer a couple of these burning questions. Leads us to the conclusions, and we will have, of course, time for residual questions. While this webinar gave you this very broad overview of applications, it can be applied to physical, chemical, or electrochemical biological systems of small scale, big scale, but also other systems shouldn't be reactor systems. Flow distribution, storage. It's not used sufficiently yet in the water industry. This is why we are giving these webinars, for example. Each group has different needs and benefits. So if you look at the 3 end users, let's say, like end users, chemical companies or utilities operating the systems, consulting and engineering firms, technology developers and vendors, each of them, of course, all of them are interested in having the best technology and performance, but each of them have subtle differences. Yeah. For example, here the energy saving is important. Time in a project is important for the second category, and of course here the time to market matters. So there are some subtle differences that should be understood. But we have seen in all of the projects we have been doing, we have now been working, I think, on more than 150 different projects, while the benefits of proper applications of computational fluid dynamics are really significant. Yeah? That's what we can say after running really a lot of cases with our team. Okay, so for the people that would like to leave now, well, I would like to thank you for joining us today. It was an honor to having you here. Please get back to us, send us your more questions, but don't forget to fill in the questionnaire. Connect with us on LinkedIn. So this is really our main platform where we share a lot of our content and updates. But of course, stay with us for a couple of more questions. So I will go back to Celia and see if there are more questions to be answered.
Thanks, Wim. No, for now, there are no additional questions.
Okay. So somebody last minute question from the hardcore audience staying until the end. This is the moment. If not, yeah, okay, we have another question. Okay, I can read it, Celia, because I saw it appearing. So the question is from Jose, are the simulation calculations based on only physical parameters, for example, speed, dimensions, flow rates, or also on chemical parameters? Very relevant question. For if we don't use kinetics, we only need some 2 categories of data: geometrical data, size, basic data, and flow rates. Flow rates of water, and if you have aeration, for example, aeration flow rates. That's physical. If we have kinetics, yes, we include the chemical and the biochemical parameters. For example, we did a lot of chemical plants. One of those plants had very high salinity. So also TOC, so total organic carbon, was much more relevant than COD, chemical oxygen demand, because the chlorides interfered with the COD test. So we had to do model modifications, and we just calibrated our model based on that specific wastewater. If we look at municipal wastewater, is exactly the same. If we look at disinfection, we will include chlorine disinfection kinetics. If we look at ozonation, we will include the chemical conversion rates of micropollutants or the disinfection rates of viruses and bacteria or other indicator organisms. So yes, we have a lot of cases where we include the chemical or biochemical parameters as well. It really depends on the question. Yeah. So Celia, are there other questions?
Yes, there's an additional question. As we are active in the wastewater sector, if you have any cases for anaerobic digestion where our kinetic model is time dependent.
The kinetic model time dependent. I'm not sure if I get the last part. But what we have done is we have mainly been looking at mixing in anaerobic digestion. So these were mainly mixing issues. Yeah. So high viscosity is so-called non-Newtonian. Non-Newtonian. The more you mix, the more the resistance gets. The higher your viscosity. Viscosity is not constant. So we include these parameters and then look at the mixers. Especially, it's always about heat transfer either, or mixer location or type, or recirculation loops in such systems. Yeah. We have been working on implementation of kinetics, Usman, and I see you joined again. Maybe you can briefly talk a bit more about that. Huh?
Yeah, I just wanted to comment on the transient question, the time dependence of the kinetic model. It's definitely possible. What we have done in the past with a very simple ADM1 model for the digesters, we have done, it was together with the University of Ghent that we did some time dependent analysis. But we figured out actually, if you are working in a steady state situation, you would eventually come to the same conclusions. So we didn't find in that particular case it to be very useful to do time dependent. But if your question is, can we do it or should we do it? It's a bit different. Can we do it? Yes. Should we do it? It's up for a bit of a debate.
Yeah.
Yeah, maybe an additional question, I think it's already answered, but I want to make sure, is that if we can do simulations in a non-Newtonian liquid. I think, yes. Usman or Wim, I don't know who wants to answer.
Yeah, well, actually, the CFD takes really into account the viscosity, so that is really modeled. And then if you have shear thinning happening, which leads to different local viscosities, it definitely can be taken into account. What CFD does is that it takes into account the shear. So what is your local shear? Based on it, it can predict the local viscosity and eventually the flow field. So it also, for example, depends what are other constituents of your system. If it's an impeller, for example, you will have different viscosity close to the impeller, and close to the walls it will be much different. If you have, for example, bubbles, in the vicinity of the bubbles, you will have different shear leading to different viscosities. If you have highly turbulence or non-turbulence, you will have very different viscosity regimes.
Okay.
Yes, I think we have handled all questions. Maybe time for one last if someone still has a burning question. Now is the moment.
Yeah, maybe I have a last one, Celia, for the audience. So if you can please fill in the feedback survey that pops up normally after closing this window, that would be awesome. Yeah. So yeah, if you have any more questions, feel free to just send us an email. You will just reply on the email sent in the framework of this webinar, and we will get back to you. So yeah, so on behalf of the whole team, I want to thank everybody here for joining us and for staying so long, because staying for 1 hour in a webinar is not easy, and we have many, right? We have many webinars these days. So yeah, thanks a lot for joining, and we hope to get in touch with you again. See you next time.